Okay, I'm going to try something that Mr. Smith has done a lot, which is integrating live video with narrated PowerPoints, but not something that I've done much of. So you'll bear with me if this is brilliant, but we'll give it a go. So we're going to have a look today at magnets and magnetism. And my plan is that we'll have a look at the idea of magnets and the idea of ferromagnetism. We'll talk about domains, which is how sort of magnets form. We'll talk about soft and hard magnetic materials, the field lines around a single magnet, the field lines around between pairs of magnets. And these two, you have to make sure that you have copies of in your notes. They are really important, so make sure they're in the notes. And I think you should really take some notes and draw some of the illustrations of domains as well. And then I'm just going to briefly talk about the fact that field lines are three-dimensional objects. Okay, so let's have a look at magnetic materials. Now, magnetic materials come in different sorts. And the magnetism is a result of a electric current, and we'll talk about that a bit more, how you can actually use electric current to produce magnets. But Mr. Smith walked in and he's desperately closing the door really quietly so you don't hear him. The magnetism arises from current. Now, you can all imagine that atoms have little electrons going around them, and if all the electrons line up, then we get an electric current as the goes around. So some atoms have magnetic properties. And most things actually have some sort of magnetic property. It's just that when a magnetic field is brought close, they line up against it. So the end result is not dramatic. They try and reduce the strength of the magnetic field, and so nothing very interesting happens. There is one kind of magnetic material, however, called ferromagnetism, where when we put a ferromagnetic material into a magnetic field, it actually lines up to enhance the field. And you get dramatic effects because anything ferromagnetic put into a magnetic field temporarily becomes a magnet itself as it lines up trying to enhance what's going on. And you might know from your chemistry that ferro comes from the Latin word for iron. And so the obvious ferromagnetic material is iron. Now that's a piece of iron. It's not a magnet. Hasn't been magnetized, and even if it were magnetized, because it's iron, what happens is iron tends to relax back from, when you magnetize it, tends to relax back and end up being demagnetized after a while. This, on the other hand, is a piece of steel. Steel has, the vast majority of steel is still iron, but there's other things in there as well, particularly carbon. And so the composition of steel means that when we magnetize steel, when we put it into a large magnetic field, it stays magnetized. And so we refer to steel magnets as permanent magnets. So steel is a permanent magnetic material and sometimes called a hard magnetic material. So that's a steel bar magnet. You can see it's got a little notch in the corner. I hope you can on the video anyway. It's got a little notch on the corner, and that tells me that the side with the notch has been set up, so that's its north pole. I'm sure you played with them in primary school and you know that magnets will have a north and a south pole. That's north on there. The strength of the magnet largely depends on the volume of iron you have. So if you have a larger volume of iron, you have a slightly stronger magnet. And up until 20, 30 years ago, that was it as far as magnets were concerned. They were largely made out of steel or out of materials called ferrite, and were largely based on iron. Today, we have, much more commonly than they ever were before, we have magnets, permanent magnets, that are based on a different chemical. They're based on the element neodymium. They're not entirely neodymium, it's a compound, but neodymium magnets, I'll bet some of you, quite a lot of you have actually owned some neodymium magnets. Neodymium magnets very much stronger than the iron ones. I'll do that with a bit of iron. But I don't really care about my bolt. I'll do it with a neodymium magnet, and you'll see the neodymium magnet will take off and attach itself. Much stronger magnet. And so today we largely use neodymium permanent magnets, and sometimes called rare earth, because neodymium is a member of the rare earth metals, which on the periodic table there's two stripes that stick out off the bottom of a periodic table that you never know what they are, because you don't even cover them in A-level chemistry. So they just sit there and you ignore them, and the chemistry teachers don't tell you anything about them. Well, they're known as the rare earth metals, and neodymium is one of those. And so samarium also has magnetic properties. There are other sort of more ordinary ferro magnets. Nickel is ferromagnetic, and so I don't know how much you can see of this. You can perhaps see the grey compound, neodymium compound inside there, and then it's been coated in some nickel, and the nickel coating is just to provide the compound with some protection. And of course, the nickel being magnetic, it adds to the overall magnetism of the thing, but the main reason for the nickel on the outside there is just to protect, and you can see nickel's chipped off this one, and the sort of softer ceramic compound of the neodymium is exposed inside. And that's really the danger with these magnets, is that occasionally they can shatter because they do leap about a bit, and occasionally they'll shatter because it's a ceramic, like a teacup, inside, and so occasionally those shards can be quite sharp. There's no other real danger in messing around with neodymium magnets, unless you've got really big ones, in which case you get your finger trapped between them. It hurts like hell. I know that. I've done that with ones at university that have been incredibly painful. Okay, so I mentioned domains in the bit of video there. Domains are areas within a magnetic material that have a particular magnetic orientation. And there is a type of microscopy called Kerr microscopy that allows you to actually see the domains. And so that's what this is a picture of. What we've got here is, this is a piece of a close-up of a neodymium magnet. You can see the individual grain boundaries. See the grain boundaries there? But they aren't the domains. The domains are these stripes. So a dark coloured stripe has its magnetic field orientated in one direction, whereas a light coloured stripe has its its magnetic field orientated in the opposite direction. And the reason that magnets do this, or magnetic materials do this, is that if it's a ferromagnet, it wants to line up all its magnetic fields. All of the atoms that make up the material, their magnetic fields will line up, and so you're automatically going to get regions where everything is pointing in one direction. But the material as a whole doesn't particularly want everything to line up, because that's energetically costly. It's sort of a higher energy state if all of its domains have lined up. So the way that a magnetic material solves this conundrum, having the atoms all wanting to line up, but not wanting to line up overall because that's a higher energy state, is by having areas within each crystal that are pointing in opposite directions. You can see that one's probably pointing that way, and that one's pointing that way, and that one's pointing that way, and that's within one crystal, and then the neighbouring crystal is doing something else altogether. This one here has been highlighted. I've taken this picture from Wikipedia. This one here has been highlighted because actually the magnetic field orientation on that particular grain are going in and out of the page. So some of them are pointing down into the page, and some of them are coming out straight out of the page. These ones are going along the page. These ones are actually going in and out of the page, which when we do magnetism, we indicate with crosses. So domains are areas within a magnet that are within the area of the domain, or the magnetic field is aligned in one direction, but the neighbouring bit of the domain is probably aligned in a different direction. And here's the illustration that we usually get you to draw in your books, so therefore I would suggest you put in your books. Obviously you can use an S and not a Z, because I took this from an American website. And so beforehand we have our domains. This is really assuming that one grain boundary is one domain, which we've just seen on the previous slide isn't true, but overall it's good enough. Basically, the areas of magnetism within our magnetic material are all randomly aligned, so that overall our magnetic material is not magnetic, is not a magnet. But if we magnetize it, we can force those domains to line up. And if those domains all line up, we've made a magnet. Now, usually what we do is we induce magnetism, i.e. we get some of the domains to line up with the magnet we're bringing close, and that's good enough to cause the magnet and the piece of iron to stick together. So that's induced magnetism. Or we can go to full-on making it a permanent magnet if we can get them all to line up, and it is a hard magnetic material, which we'll talk about a bit more later on. So this is the idea of induced magnetism. Our iron nails or our steel paper clips are not in and of themselves magnets. This is a magnet. They are not magnets, but because we've brought them close to a magnet, because we've brought them into a magnetic field, lots of their domains within the bit of iron or within the bit of steel will start to line up, and they'll line up so that they attract to the magnet we've brought close. So in our iron nails, for example, we get north at that end and south on the other end, because that means north is attracting to south with our magnet. So our induced magnetism is induced in such a way that it attracts to whatever's doing the inducing. And you can see it will carry on. That's a north end, that's a south end, that's a north end, so that all of these iron nails are all being attracted to each other, whilst there is our big magnet there inducing magnetism within all the iron nails. But because iron is not a hard magnetic material, and because we've probably only aligned 70% of the domains within the iron, when I take the big magnet away, it'll relax back, and these will no longer be magnetic. Steel, on the other hand, is a hard magnetic material, and so potentially when I take the big magnet away, these could still be magnetized, but they probably won't be, because the magnetic field of just an ordinary bar magnet is probably not strong enough to permanently magnetize our steel. So this will be induced magnetism in our paper clips. Just you notice it's the other way around, because now we've got south attracting to north, south attracting to north, south attracting to north. Okay, not massively important in year 9, but this does turn up in the GCSE. In which way, where will the north and south pole be on an induced bit of iron brought near to a magnet? And the answer is the north and south will be on the sides that mean that it attracts towards the magnet doing the inducing. Right, soft and hard magnetic materials. Actually, this page isn't soft and hard magnetic materials, it's magnetic materials in general. And so ferromagnetic elements. So which elements are ferromagnetic? Well, we all know, because I've talked about it on the video, and you probably know already, that iron is. Well, it turns out nickel is, and cobalt is, and to a lesser extent, some rare earth elements that you're not going to have heard of: gadolinium, terbium, and dysprosium. I've used gadolinium. It's a very pretty pink oxide. So they're the elements that, if you refine out the element, it turns out to be ferromagnetic. Not many, when you think there's 90 odd elements commonly occurring. And then compounds and alloys, steel. So steel, I hope you know, is mostly made out of iron, so no surprise that steel is magnetic. But oddly, when you put in when you change its structure by making it stainless steel, you put in a few other things, and that changes its overall structure. A lot of stainless steels are actually not magnetic. One of the things you can do is tell how good a stainless steel is, whether it's magnetic or not. Normal iron oxide is magnetic, but iron can take several oxidation states, so not all iron oxide is magnetic. Chromium oxide, and then you can start getting some odd compounds by mixing odd things together that become ferromagnetic, like manganese and bismuth. 50-50 mix of those two will give us a ferromagnetic material. The most naturally occurring mineral that's magnetic is magnetite, and it used to be called lodestone. I don't know, maybe you like history more than physics. If you like history, you might have read about lodestone being used as compasses in the really early sailing. There's some suggestion that that maybe even the Vikings got hold of lodestone and could use that, therefore, to know which way was north. So lodestone is a naturally occurring magnetic material called magnetite, but it's not actually ferromagnetic, it's ferrimagnetic. In lodestone, for every 3 atoms, 2 of them aligns and 1 doesn't align. So that means it's not quite as strong as a ferromagnetic, because in a ferromagnetic, all 3 of them would align, whereas in our ferrimagnetic material, 2 of them align, 1 doesn't, which overall ends up with sort of you having the effect of maybe only having 1 aligned. So ferrimagnetic. Don't need to know that for any exam that I've ever come across. It's just interesting. And then the rare earth magnets, based on neodymium, NiB, or based on samarium. These are the super duper magnets that we all like to play with, much better than any of these things. Then soft and hard magnetic materials, just iron. So just iron, the element, is ferromagnetic. Well, it has to be because it's named after iron. But it's a soft magnetic material. That means when we induce magnetism within it, and then we take the inducing magnet away, it'll relax back to being unaligned. So it's a soft magnetic material. It will carry a magnetic field. It will enhance a magnetic field. All of the iron atoms will all line up to enhance that magnetic field. So it's very useful for enhancing magnetic fields. But when we turn the magnetic field off, take the magnet away, it will relax back to being unaligned. And that turns out to be really useful when we get onto electromagnets. Steel, on the other hand, is a hard magnetic material, or actually, in truth, harder than iron. Not all that hard a magnetic material. There are ways of making much harder magnetic materials. And the idea behind that is that once you've got the majority of the domains in a hard magnetic material aligned, they stay aligned. So you make a permanent magnet. So you can make steel into a permanent magnet, whereas you couldn't make a bit of ordinary iron. And the difference between basic steel and iron is how much carbon there is in them. You can, because of the carbon, because of the way that the steel gets rolled out, so its crystals will tend to align with one another, steel is a harder magnetic material and therefore will stay as a permanent magnet once you get the majority of the domains to line up. Alignment can be achieved by putting the steel into a really strong magnetic field. So if you put it into a strong electromagnet, after you took it out of the strong electromagnet, you'd find you had a permanent magnet. That's how they're made. You can also do it. This used to be the sort of thing that I used to do as a kid. It's not something I guess many of you bother doing anymore because you've got an iPad to play with. But you can take a piece of steel, and if you repeatedly stroke it with not a particularly large magnet, but if you stroke that magnet along the piece of steel and you always stroke it in the same direction, and you just keep on doing that, eventually you convince all of the domains within the steel to all line up in that same direction, and you can make yourself a permanent magnet. So you can make nobody carries a penknife anymore because the police would stop and take it off you. But I used to carry a penknife, and I could make my penknife magnetic. And then heating the steel or hammering the steel will cause the domains to relax back to being unaligned. You can imagine heat is adding energy in, shaking the thing about, and it will relax back to being unaligned. And hammering does the same kind of thing, shakes it all about and puts a bit of energy in and allows it to relax back into its lower energy state, which is to have the domains all mixed up, like in that slide I showed you earlier on with the KMS microscopy. Right, magnetic field lines. Now, this is the idea that we know that magnets have an effect at a distance. Two magnets don't have to be right touching each other for them to affect one another. And that's called action at a distance, or a field. And so our magnet has a field that reaches out into the space round about it, influencing the things around it. So if it finds another magnet having reached out with its field, the two magnets will influence one another. And the Earth has a magnetic field, and so all magnets are somewhat influenced by the magnetic field of the Earth. which is how compasses work. And we denote a field, we indicate a field with field lines. So we draw lines that indicate how a field is acting. Basically, the lines tell you, if I put another magnet there, where would it go? If I put a bit of magnetic material here, that would tell me that the north would go off in that direction. If I put a bit of magnetic material here, it wants to go off in the north wants to go off in that direction, the south wants to go off in that direction. So the end result probably is that it ends up going that way. So field lines tell us about how the field is reaching out into space. And field lines are really easy to visualize with magnets, and you've probably done something like it in year 6, but I'll cut to a video of me messing around with it now. Now, the other thing that you know about magnets, I'm sure you've done this before, is that they have a magnetic field around them. So if I take my magnet, place it under a piece of paper, and then bring my iron filing shaker near it. Iron filings, so clearly ferromagnetic material, not magnetised, but so won't attract my iron bar, or won't attract my bolt. Don't attract my bolt. Are on the other hand attracted by my neodymium magnet. Can you see them following the neodymium magnet up the sides there and chasing it around? So, let me just pause it. Okay, keeping going. You've seen this before. I'm sure you've done this before. There you go. Can you see that my magnet immediately appears in the iron filing dust? Now, more importantly, a pattern appears. Let's see if I can move my phone so you can see it. There you go. We get a pattern of loops, and the loops run from the North Pole around to the South Pole. And that's once one loop has gone from north to south, it then will repel the next loop that goes from north to south. It will repel the next loop that goes from north to south. Because all these iron filings have lined up to try and enhance the field. And so they've all lined up in line with the magnetic field being produced by our permanent magnet. But of course they all repel each other because they're all orientated the same way. And so we get these stripes appearing where we've got a whole little line of iron filings lined up with the field, and then a bit of a gap before we get the next one. And as I say, the field lines loop from north around to south. They try and take the shortest route. And then these ones up here, there is no short route round to south for these ones that are coming out the top here. And so those ones will have gone and found themselves something else that they can sort of attach those field lines to, which is almost certainly the iron underneath this table. And so magnetic field lines always travel in loops. They always connect from north to south, but the south doesn't have to be the south on their own magnet. It can be somewhere else entirely. Okay, so I've reset things now, and I've got a pair of magnets with the north facing a south, so they're attracting each other. I've got to have them that far apart. If I have them any closer together, they slide together. I'm then going to cover those up, and we'll have a look at the field lines that occur. Okay, hopefully you can see that we get a dense set of field lines here because this is a really easy path from north to south in that gap. So we get a really dense set of field lines in that gap running from north to south. But as I say, they repel each other, so they start bowing outwards towards the outside edges. And then we get the rest of the field lines very much like they were for the single permanent magnet roundabout. But where they're attracting, we get this intense set of field lines. Now, I always think of magnetic field lines as being like little rubber bands that repel each other. And like all rubber bands, they want to snap back to being as short as possible. And so I think of these two magnets as attracting to one another because those field lines, that intense set of field lines between them, want to snap back and close that up. And so, how good an analogy that is, I'm not certain, but it's the way I tend to think about the field that surrounds the magnets, the way that the magnets themselves reach out into space. Okay, I've reset it once more, and this time I've got a pair of norths facing each other, and you can see that they don't want to be a pair of norths facing each other. It wants to swing around so it's a north and a south facing each other. They are definitely unhappy with that configuration and are repelling. Hopefully you could see all that in the video. So if I put the paper back over those, do you spot that there's nothing wants to go in this middle space here? Anything that dropped on the middle slid away instantly. That's where it's repelling, and the consequence of the field lines strongly repelling one another is we don't actually get any field lines sitting in the middle. We'll get any of the iron filings trying to line up with the field in the middle, because there really isn't a field in the middle there other than one pushing away. They're strongly repelling in the middle there, and consequently we end up with no field lines sitting in the gap. The field lines all curving away, being pushed away from one another, attempting to get from these norths back round to the souths. They can't go across the gap. Now, the other thing I want to show you, I'm just going to put a lot of iron filings on one pole here. We'll see if I can get it to show up on the screen. Yeah, it's just not focusing for me right at the minute. There we go. Now, can you see that the field lines are slightly three-dimensional? That this pile of iron filings here wants to sort of reach up out into space as well as following the field lines in flat 2 dimensions. Can you see the sort of little set of spikes? How well it's showing up on my computer screen. See that little set of spikes reaching up into space? Field lines are a 3-dimensional thing. Of course, whenever you see them as 2-dimensional, because somebody does it with iron filings on a bit of paper like this, or you're looking at a drawing of them, you never really see them as 3-dimensional things, but it is important to understand that they are 3-dimensional things. Now, I don't know whether you can see it on the screen there, but I've coated everywhere in iron filings, and that's got 2 issues. It's horrible and gritty. But if you've got it on your hands and then wiped your eye and got the iron in your eye, the iron could theoretically damage your eye. So we want to make sure that the desks get cleaned up of those iron filings. And the simplest way to do it is to wrap a bit of paper, wrap a permanent magnet in a bit of paper, and then just take a bit of paper over the top of everywhere. You hear it scraping. And there's the iron filings I picked up off the desk onto my bit of paper that I'll now bung in the bin and not leave on Mr. Smith's bench. Okay, this is the bit that is required, so you need to make sure you've made yourself some notes in your book here. I thought the complicated picture a couple of slides ago was actually the better one of the way that field lines behave, but this is the sort of next best one I could find that was relatively simple without too many lines for you to have to copy. So please pause the video, copy this down with this title. Make sure you've put the arrows on, and make sure you do a decent job of it. The field lines, notice none of the field lines touch. I think of field lines as being like little elastic bands that are repelling each other. And as they're all repelling each other, but they always want to take the shortest distance back to between north and south, they end up not touching. So do not draw yours so that the field lines are touching. There's a gap between all of them. Okay, so pause the video and make sure you've got a good job of copying that out into your books. Okay, you saw in my video field lines doing this for 2 attracting magnets. I don't massively like the kink in this particular picture that I found on the internet, this sort of kink there. I would prefer these were smoother curves running from one to the other without the kink. But your main job, once again, is to make sure you mark the arrows in and make sure the field lines don't touch each other as they curve round. So getting this diagram in and indicating that there's lots of field lines in this gap between north and south. Strong field where north and south are approaching each other is your job in reproducing this one. If you think about how the field lines showed up when I did it on the live video, then you'll have a good idea what it is you've got to be drawing. So once again, pause the video and do a decent job copying that with this title into your books. Okay, final one that you've got to copy is this with them repelling. Now you remember me saying on the live video that there's no field in the centre there where they're repelling. All the field lines are pushing each other away, and these north field lines and these north field lines really do not want to come close to each other, so they're I'm sorry, they're repelling one another, leaving this sort of gap in the centre there where nothing wants to sit. Where you saw that when I put my iron filings into that space, they bounced away from that space and they lined up with these field lines over here. They didn't want to sit in this space in the centre. So once again, do a decent job of copying that into your books. Last one you've got to do, copy that into your books with that title, please. Now, I never tried this on screen before, but you've probably seen it because it turns up on the TV quite a lot. And that's this thing called ferrofluid. And ferrofluid is an oily fluid that has iron suspended within it. And the advantage of that is it's a much more effective way of showing up the three-dimensional structures of the field lines. Unfortunately, iron stains things really, really badly. You may not realise, but actually all the sort of reds and the yellows in oil paints are all based on iron. And those oil paints, they'll stay permanently that yellow, brown, red colour pretty much forever because the iron stains things. And you can see this glass container that we use for that is totally stained by this material. So if you think I'm being a bit overcautious with this stuff when I'm playing with it, it's not because it's toxic in any way. It's because if I get it on my hands will be brown until that bit of skin on the surface of those hands dies and falls off and takes the iron with it. And if I get it on Mr. Smith's desk, we'd have to polish the surface of the desk back off to get rid of the brown stain. And if I get it on my clothes, those clothes just have to go in the bin because the brown stain will be there forever. But let's have a look. I'll perhaps use a bit of paper just to not completely wreck Mr. Smith's desk as I spill it. It's horrid stuff. But it does do this demo beautifully. I don't know whether you can see that there's just a sort of glossy black liquid in the bottom there. Normally I keep it in here because I don't want to risk spilling it, but today for the video I'm going to pour it out. There you go, glossy black liquid. Hopefully you can all see that on the screen there. And I've just got to try and not spill it. Okay, slightly chunkier steel magnet. Now, if I put the steel magnet behind it, can you see? I don't know how well it's showing up. There you go, you can see it there. If I take it away, bring it back. See those spikes? Those spikes are the iron, the ferrofluid, the iron in this fluid, attempting to follow the field lines around in the way that the iron filings followed the field lines around. And the consequence is that the fluid actually lifts up into spikes where each spike represents a field line going off into space, and the iron liquid trying to follow that field line up and around space. So it gives you a good idea of the three-dimensional nature of the field lines. It's also quite beautiful. And I say, now you've seen it on the video here, you probably realise you've seen it on the TV. I think it's Sky Arts. Maybe you never watched Sky Arts. Sky Arts uses this effect in lots and lots of its trailers. And if you go onto YouTube and you put ferrofluid in, there are some amazing ferrofluid. Where there's one I know, can think off the top of my head, where they have a bolt that's magnetic, and the ferrofluid follows the helix of the bolt thread up, and then goes into spikes when it arrives at the top of the bolt. It's absolutely beautiful. So if you've got a bit of time, have a look for ferrofluid videos on YouTube. They're amazing. So that's with my steel magnet, my basic steel magnet. I switch that for my neodymium magnet. I'm putting the bolt on here, not because I'm going to do clever things with ferrofluid and bolt, but because the bolt just makes holding the neodymium magnet a whole lot easier. Okay, hopefully it's back in position where you can see it. There you go. Now that, I hope you agree, is properly a thing of beauty. That's the field lines from the much stronger neodymium permanent magnet. And you can see you've got a lot more field lines, a lot more spikes, a lot more field lines, much more intense magnetic field. And the ferrofluid trying to follow that magnetic field gives us a really nice visualization of the fact that those field lines are zooming off out into space. I turn it so that my neodymium magnet is like that. This one has the north and the south on the faces. So if I have it so like that underneath, you see, you just get this very smooth bulge. You can see that on the screen there. You get a smooth bulge. And that, of course, is the field lines doing that curve that we saw in the iron filings, where it curves around from the North Pole around to the South Pole. And that smooth curve that you can see in the IR ferrofluid there is exactly the same thing. That's those field lines curving around from the North Pole to the South Pole, whereas that is the poles themselves. That's the field lines going out into space, looking to get to a South Pole. Really lovely stuff to play with. Now it'll even follow it up the sides of the container, so it defies gravity. And this is the point where I always end up spilling it out and getting it over myself, so I'm going to restrain myself. Can you see that neodymium magnet is so tightly attracted to the iron ferrofluid that it's sitting there quite happily? I haven't glued that or anything. That's just the attraction to the ferrofluid. And if I bring up another one, I've got another one, second one on the other side. So the two are attracting across. You can see the field lines spiking out from one to the other. Just going to turn this one over, see what difference that makes. Nothing that we can see. They're too far apart to be really influencing each other. There you go, set of spikes. Set of spikes. Clearly, this second neodymium magnet that I've picked up here has been bashed around a whole lot less, because I don't know how well you can see it on the video, but it's producing far more spikes than the one on the other side. Fewer spikes over there, very many more spikes over here. So this is the stronger magnet, and that's what happens to permanent magnets. As they get bashed, they lose the magnetism. The energy you're putting in by bashing them is enough to cause them to relax back, to not be having all of their magnetism lined up. I said that iron would automatically relax back so that all its magnetism wasn't lined up, and that permanent magnets wouldn't. But if you thump a permanent magnet enough, a permanent magnet will relax back. You've given it enough energy to allow it to relax back and become just a piece of neodymium compound again. And clearly one of these has taken more of a bashing than the other one, judging by the number of spikes the two of them are producing. Okay, that was a very fast introduction to the idea of magnetic fields. I hope you've got notes on domains and decent images of the magnetic fields recorded in your notes, because that stuff is important. And if you're doing this for your GCSE course rather than your Year 9 course, I hope you've made some notes about how induced magnetism works. And so I left you on the live video with field lines being three-dimensional objects. A couple of pictures here. This is a computer model of how field lines work, and is a three-dimensional computer model of how field lines work. And of course you saw a bit of this on my video, but watching the video back, I realized that my camera did not focus all that well on these beautiful spikes that you get when you put ferrofluid above a strong magnet. You can see this is a strong neodymium magnet on the bottom there, this piece of glass, and then we got some ferrofluid sitting on the top making these amazing spikes. So perhaps a better picture than you managed to get from looking at the video, because the focusing on my camera wasn't always doing everything it wanted to do. Okay, so that's permanent magnets and magnetic materials and permanent magnets. The next topic will be electromagnets.